All right, guys, let's start. Okay, so today we are doing your new topic, linear algebra. Here we are. First topic is very easy. The subtopic is very easy. Basically, chapter 1 is about your introduction to linear algebra and your matrix operations, right? So, I think every one of you who has passed high school, right, and gone to senior secondary and then colleges and even done masters, right? You have a fair bit of idea about linear algebra as well as your matrix operations, right? Today we'll talk about basics of linear algebra in your quant finance. Okay, so that's the whole idea. Okay, now when we talk about basics, right, please understand, especially in linear algebra, right? So we are studying what we are studying here. You're trying to understand this in perspective of your quant finance, right? So please understand, in quant finance we rarely deal with one asset, one return, or one risk factor. We deal with hundreds of assets, thousands of prices, and multiple risk factors, your correlations, your volatility, your constraints. Linear algebra is a language that let us compress all of this into your clean mathematical objects, right? So vector is equal to list of numbers, matrix is equal to table of numbers, equation system is nothing but many unknowns solved together. That is why when you look at your portfolio theory, then we look at your factors model, when you look at your PCA risk models, right? Regression, derivative pricing, all depends on your linear algebra. Okay. With that, let's start. Okay. Now, when you talk about linear algebra, please understand very, very clearly, right? Very, very clearly, linear algebra is the branch of mathematics that studies your vector, your matrices, your linear transformation, and structure relationship, right? What are vectors? Vectors are basically your one-dimensional arrays. For example, like your portfolio weights, your asset return, your risk exposure. Your matrices like your two-dimensional arrays, your covariance matrix, your correlation matrix, your return history. Linear transformation is about how one set of numbers transform into another. Example, risk factor exposure transforming into your portfolio risk. In quant finance, the real issue when you look at, right, is scale. You may have 500 stock, you may have 20 risk factor, you may have 10 years of daily data. You cannot handle that manually. Linear algebra gives you a structured way to model the system. The simple idea is that a portfolio in Indian context, right, it's not just about few stocks like your Reliance, HDFC, or Infosys. It's a vector of weights, right? Multiply a vector of or the matrix of your returns and risks. That is the quant way of thinking, right? So linear algebra provides you efficient tools to model and solve problems involving large data sets, many variable, portfolio optimization, risk management, asset pricing, and regression models, multi-asset system and market relationship. Key topics in this lesson with vectors and matrices, which are the building blocks of financial data. I told you, system of linear equations, solving multi-variable problems, and application in finance, pricing, risk, and portfolio construction. Okay. Simple, straightforward. Next one, when we go into, next one is your vectors in quant finance. Now, when you talk about vectors in quant finance, please understand very clearly what is vector. Vector is an ordered list of numbers, right? Ordered list of number used to represent your multiple financial quantities at once, right? So it can be written like this, right? Just for example, right? I am taking the returns, right? Let's say I'm taking the return as 12, 8 minus 4. What does it mean? It means that asset 1 return is 12%, asset 2 return is 8%, asset 3 return is minus 4%. Right? Very simple, very straightforward. Very important point here is that order matters. Right? If one asset 1 is Reliance, asset 2 is HDFC, asset 3 is Infosys, then every model must preserve that order, right? Preserve that order, right? So common finance use of vectors, asset returns, return on multiple assets in one period, portfolio weights, allocation across assets, risk factor, interest rate, volatility, and macro exposures. Right? Now, there are more, right? Your expected return, sensitivities like delta, duration, beta, right? For example, portfolio weights would be whatever, right? Equal to your 0.5, 0.3, 0.2, right? This means 50%, 30%, 20% allocation. The moment you write finance data as vector, you can calculate portfolio return very, very cleanly, right? Because what is the portfolio return in that case? Your return of portfolio becomes what? You take the return of portfolio as weight, and your R, right? So that is the beauty of quant finance, right? Complex portfolio logic becomes your compact mathematics. Okay. So this is a finance example. These are different returns which I have written above, right? That's what we see. Then we go ahead. Then we talk about your matrices in your quantitative finance. We talk about matrices in quantitative finance. What is matrices? Matrices or matrix, right? Matrix is a table of numbers arranged in rows and columns, right? In finance, matrices matter because relationships are not one-dimensional. Assets move with other assets. Risk factor influence many securities. Return change across time. Covariances exist between every pair of assets, right? Now, matrix is a two-dimensional array of numbers arranged in rows and columns. Why matrix matters in finance? Matrices help represent relationship across multiple assets and multiple variables efficiently. Common use include covariance matrices, correlation matrices, risk factor models. Covariance matrices means what? Measures how assets move together and quantify your portfolio risk. Correlation show normalized co-investment between assets. Risk factor models represent exposure of assets to macro risk factor drivers, right? So idea is when you look at your covariance matrix, right? Simple thing is that it is measuring how assets move together, right? So assets move with other assets, right? That is very important to understand. Risk factor influence many securities, return change across time, covariance exists between every pair of asset. In finance, matrix matter because relationships are not one-dimensional. Matrix is a table number arranged in rows and columns, right? Now, for example, when I look at your covariance matrix, which I told you, right? How assets move together. Correlation matrix, it's like normalized co-movement. Now, this sounds very fancy, normalized co-movement. Like it is just that we are putting now movement in your -1 to +1, right? Then we have your normalized. So it's the value of correlation will go from -1 to +1. Covariance will go from -infinity to infinity, right? When we have your factor exposure matrix, right? Shows exposure of each asset to different risk factors. For example, if you have, let's say, 100 assets, the covariance matrix is what? 100 into 100, right? It tells you how each asset interacts with every other asset. This is central to your portfolio risk. This is central to your derivatives, right? A portfolio is not risky only because individual stocks are kind of volatile. They're risky because how they move together. That is the heart. That is why your correlation covariance are the heart of risk management, right? So that is how it is written in quant finance. Most models are written in matrix form because it is fast, scalable, and clean, right? Okay. Then we have done this. Then we move to the next part, right? So next is your asset return as matrix. When you talk about asset return as matrix, please understand is a slide is showing you return of three assets over three time periods. So R is equal to different things, right? Each this is a matrix which is showing what? Here each row is one asset's return across time. Each column is all asset returns at one time. Okay. Again, I'm repeating. Each row is one asset's return across time. Each column is all asset returns at one time. This is exactly how market data is stored in your real quant system. For example, rows can be stocks, columns can be your dates, values can be your daily returns. Once data is in this form, we can calculate your average return of each asset. We can calculate the volatility of each asset. We can calculate the covariance of each asset, right? Correlation matrix, factor regression, portfolio backtest, right? So the matrix is not just notation, it is the basic data structure behind your quant finance, right? So each row represents one asset return across time. Each column represents the return of all assets at a specific time. In finance, the meaning is matrices allow compact storage of return histories, useful for computing your covariances, correlation, and factor regression. Okay. With that, we move to the next slide. The next slide is about systems of linear equations in your quant finance. Right, when we talk about system of linear equation, please understand a system of equation does what? A system of equation basically solves your multiple unknowns together, right? For example, let's say we have an equation called 2x plus y equal 10, another equation called x plus 3y equal 50. Here, x and y represents your allocation in your two assets, right? So the matrix form when we take, right, it is kind of like this. What do you mean by this? Where W is what? W is your unknown weights, right? That is why this is W, right? Your A is your coefficient, right? This is your coefficient, right? And B is your target outcome, right? So in finance, this is everywhere. For example, when we are trying to find your portfolio base to hit a target run, when we are trying to solve for your hedge ratio, when we are trying to replicate an option payoff or constructed duration neutral bond portfolio, we're trying to solve the arbitrage free pricing system, right? The deeper insight here is that finance is full of constraint. Let's say you say that I want 8% return. I want beta equal to 0. I want duration equal to 5. I want weights to sum to 1. These become equation, right? And linear algebra solves them together, right? That's the whole idea, a Gaussian elimination, right? A solution method. Okay. So use cases we have understood, right? Solving for portfolio weights, multi-asset pricing relationship, hedging and replication problems. So once you understand, that makes sense, right? Then we get into your matrix operation in finance. When I talk about matrix operation in finance, please understand that matrix operation include your addition, oblique subtraction. What does it mean? You combine or adjust your portfolio return matrices. For example, excess return is equal to asset return minus your benchmark return. Multiplication, basically you are computing your exposure, and this transformation, what is it? Factor exposure into factor return, right? So you have right into your factor return. And this, if you want to understand addition, subtraction, what is it? It is your asset, return of asset minus your return of benchmark. Okay. That can be used for inverse also, right? Inverse means using optimization, solving for optimal portfolio weights. The key formula which we need to understand here is, right, that sigma square P is equal to WT sigma W. What is it, right? What is happening? W is what? What is W here? W is your portfolio weight, right? What is your sigma? This is your covariance matrix, right? And then when I do this, right, what is this whole pointing at? This whole is pointing at your total portfolio risk. Right, so please, this is not a summation sigma, right? This symbol is for covariance matrix, right? This formula captures your two things. One is the individual asset risk, interaction correlation between asset. This is the core of your Markowitz portfolio theory. Without the covariance matrix, you cannot properly understand the diversification, right? Major total portfolio volatility risk capture both individual risk and correlation. Core equation mean variance optimization, right? That we need to understand, right? And this is your coverage matrix, right? Then we go ahead, we talk about key applications of linear algebra in finance, right? So how the chapter joins everything together is that we talk about that the portfolio optimization, portfolio return and risk are written using vectors and matrices. You have expected return. Expected return is what? Right? Expected return, if I have to give, expected return comes out as your weight, and you have mu, right? So portfolio risk, if I have to do, again, weight, you have to take covariance matrix, right? So optimal weights require covariance matrix and matrix inversion, right? And this is the foundation of your efficient frontier, right? So that is what we understood. Optimal weights also, this part also. And please understand, when you look at a risk management, covariance matrix help measure diversification. You have eigenvalues, right? I've discussed a little bit of eigenvalues in the previous chapter. Eigenvalues and eigenvectors help identify your dominant sources of risk. PCA, since this is an introduction, I'm not going deeper. These things will be covered deeper ahead, right? PCA reduces many risk variables into a few major factors. That's a very important technique we have, right? In interest rate risk, instead of tracking every maturity separately, PCA may show that most movement come from your level shift, your slope change, or your curvature change, right? So interest rate risk, it can PCA basically decompose things into three shifts, right? Level, slope, curvature. Okay, this is directly using your market risk and fixed income risk management. And then we have your asset pricing and derivatives. What does it mean? Is that many pricing models are matrix problems. Factor model express return as what? Return as R is equal to your what? Your alpha plus beta 1 f1 plus beta 2 f2, right? And all those things. And in fixed income term structure model also use matrices to describe your income movements. So linear algebra is not theoretical; it is the engine room of quant finance, right? Please understand very clearly. Pricing model often requires following matrix system. Factor model express return as a linear combination of risk drivers, which I have shown you here, and fixed income term structure model use matrix representation of dynamics. Okay. So these are some of the use cases we need to understand very clearly. Okay. Finally, we have the summary, right? This particular slide is basically the core takeaway. What did you learn here in this small topic is that vector represents your returns, your weights, and exposure. Matrices represent your correlation, covariances, and time series data. System equation solve your multi-variable finance problems. And matrix operations basically power your optimization and risk analytics. Right? So you need to understand this very clearly. Vectors for this, matrices for this, system linear equation for this, matrix operation for this, right? Now, the final line is very important here, which is two, linear algebra is not optional in quant finance. Very, very important, very important in quant finance, right? It sits behind your modern portfolio theory, your risk models, your PCA, your factor investing, your regression, your derivative pricing, your asset allocation, your stress testing, your hedging, right? In simple words, if statistic is the language of uncertainty, linear algebra is the language of your financial systems, right? That's what we must remember, right? Portfolio optimization using your Markowitz formula, risk measurement using covariance and this, factor exposure modeling, this, pricing and hedging formula using matrix formulation, right? Okay. Then we get into the next part, right? We are trying to think about representing a portfolio as a vector. The portfolio weights are given 0.5, 0.3, and 0.2. This means 50% in asset A, 50%, 30% in asset 2, 20% in asset 3. The capital weights must sum to 1 because the full capital is allocated, right? So what do we do? 0.5 plus 0.3 plus 0.2 is equal to 1. This is called the budget constraint. In real portfolio optimization, this becomes what? This becomes this one, right? Your covariance matrix, right? Equal to 1, right? So if short selling is not allowed, we also add one more component here is that your weights should be greater than or equal to 0, right? If short selling is not allowed, right? Short selling means you can't borrow and sell, right? If short selling not allowed, right? This is the thing, right? So if short selling is allowed, weight can be negative, right? So we can have short selling is allowed, right? I'm just writing here. This is little advanced. If short selling is allowed, you can also have your weights such as like this. Ultimately, the sum of this thing has to be 1, right? But I'm 1.2 minus 0.2, right? That means 120 long asset A and 20% short asset 2. So a simple vector of weights can represent long only portfolios, your hedge funds, your market neutral books, your leverage portfolio. That is what we need to understand, right? So your portfolio weights are vectors in your RN, right? So I talked about budget constraint also, which is this. The vector implies allocation across 3 assets. Each component shows this is this. Then we go to the next part. When we go to question number 2, when you look at question number 2, what is it? Right? Basically, here question number 2, returns are given. Right? Weights are given. Now what do? We multiply it, right? This is called the dot product. This is called the dot product. Some people call it linear product also. Right? So what are we doing? We are multiplying, right? We take each asset return, multiply with portfolio weight, then add them together, and then we get your 0.096, which is 9.6%. Why this is called linear combination? Basically, because the portfolio return is literally a weighted linear combination of asset return. That means, idea is everywhere in quant finance, right? Basically, whenever we have to do a factor model, portfolio optimization, machine learning regression, linear multi-factor investing, risk decomposition, we use that, right? What is important to understand is the formula looks very simple, but the simple things are not so simple also. Mutual fund return calculations are done by this formula. Hedge fund portfolio construction is done by this formula. ETF weighing is done by this formula. Black Litterman model is there, which is done by this formula. Mean variance optimization is done by this formula. Risk parity portfolio is done by this formula. Right? Even your AI-based portfolio system eventually reduced down to your weighted linear combination, right? So that is what we need to understand, right? So this is a beautiful linear algebra idea. The dot product measures your weighted alignment, your projection, your contribution. In finance, we are studying that how much return does each asset contributes to the total portfolio. That is why we have vector algebra becoming extremely powerful in your quant system. Okay. Then we get into the next part, which is your understanding the covariance matrix. Right. Covariance matrix is this. Right. This is one of the most important objects in all of quantitative finance. Honestly, if somebody understood or understands your covariance matrix deeply, they understand a massive portion of your risk management, right? So there are two parts here, part A, part B. Part A is diagonal terms, right? Diagonal terms are what? Diagonal terms are basically your variances, right? So what are these? Basically, there are two terms, right? This is your sigma square 1 and this is your sigma square 2. Right? These are your variances, right? Variances measure your individual asset volatility, higher variance, higher uncertainty, higher standalone risk. From finance perspective, please understand diagonal is the risk of the asset itself. Off diagonal relationship with other assets, and that's why this is same. This is relationship with other assets. There are two assets, so same thing, right? Two highly volatile assets individually may still create a lower risk profile if they move opposite to each other. That is your diversification. And when you look at your part B, which is covariance symmetry, please understand covariance of xy is equal to covariance of ix, right? Therefore, we have this, right? Meaning that covariance between Reliance and HDFC, let's say, is the same regardless of your order, right? This symmetry property is not just mathematical kind of elegance, but it is critical computationally also, right? Why we care about this property as in quant finance is, please understand, symmetric matrices allow efficient optimization algorithms, eigenvalue decomposition, PCA, right? And your stable numerical computation, which will come ahead, right? So without symmetry, many portfolio optimization methods would become kind of unstable. Okay. So please remember very clearly. And let's say, for example, when a quant desk builds a covariance matrix for, let's say, 500 stocks with 1,000 bonds or multiple factors, they must ensure the matrix is kind of symmetric. Matrix is positive, semi-definite, matrix is numerically stable. Otherwise, optimize engine kind of explodes, right? This actually happens in your real trading system, right? Which you need to understand very clearly. Then we get into your next part, which is why are eigenvalues important in your risk model. I covered this in the previous topic also, to be fair, right? See, here we are entering into high-level quant finance, right? Equation, if you look at it, is given here, right? So this is the eigenvalue equation, right? Now, what is happening here? A covariance matrix kind of transforms a vector. Usually, direction changes after transformation, but some special vectors maintain their direction. These are your eigenvectors, right? The scaling factor is the eigenvalue. Okay. When you have to look at your finance interpretation, please understand very clearly that eigenvalue tell us how much variance or the risk exists along a particular direction. Large eigenvalue is equal to dominant source of risk. And when you look at your PCA, right? PCA basically, PCA, you need to understand that you need to figure out that do you really have 500 independent risks? No. Most stocks move because of a few dominant risks. Maybe those can be your market risk, interest rate, inflation, oil, economic growth, credit stress, etc. So PCA's aim is to identify your three dominant hidden drivers, right? So they say that those three are enough to tell you about 99% of the risk, right? Massive application in quant finance is the PCA used in your interest rate modeling, your yield curve analysis, your factor investing, your statistical arbitrage, your risk compression, your hedge fund factor analysis, your volatility surface modeling, right? So famous example I can give you here, famous fixed income example in bond market, yield curve movement mostly happens in your three models or three modes, right? Basically, you have, I told you, level shift, your curve change, and your curvature change. So these three factors describe 99% of things, right? These emerge naturally from eigenvalue decomposition. That is the beauty of linear algebra. The deeper idea here is very clearly that modern quant finance is often about your reducing complexity into your dominant dimensions. Eigenvalues are the mathematical machinery behind that reduction. And, we can also use it for this factor decomposition, which I told you, right? Then once we have seen this, we get to the next part. We try to solve another question, which is solving linear systems in arbitrage. Basically, idea is that we can have two equation. You have 2x plus y, x plus y, x plus 3y, 2x plus y equal to 5, 3x plus 3y equal to 7. We solve for x and y, right? X is equal to 1.6 and y is equal to 1.8, right? Why does it matter in finance? Basically, idea is that because pricing and hedging are fundamentally system of equation. Whenever we are doing anything, right? Let's say we are doing your option application. You want to replicate an option payoff using a stock and bond. You solve equations to find your hedge weight. This is exactly the structure, right? So we take the structure of A, right? This structure, right? Which I told you earlier also, where A is the market structure, W is the unknown kind of hedge position, X for X and Y, and your B is your target. And this structure appears everywhere. When we have to look at your hedge ratio, how many future contracts hedge this portfolio, you solve the linear equations. When you look at your risk neutral probabilities, binomial option pricing, again linear system. When you look at no arbitrage pricing, modern derivative pricing is based on solving systems under no arbitrage constraints. So extremely important is to understand that a huge amount of finance boils down to find your weights, satisfying your constraint. This is your linear algebra, right? Which we need to understand. So this is what we have to understand very clearly. Okay, then once we have seen that, we go into the next part. The portfolio weight vector is written as like this, right? So these are checking your conceptual understanding. What does this vector represent? See, correct answer here is your B, portfolio allocation across your assets, right? Why? Because when W is equal to, in bracket W1, W2, W3, it represents your proportions invested, right? Portfolio management is fundamentally your vector management. Large institutional portfolios are just gigantic weight vectors. For example, if you are looking at a BlackRock or Bridgewater portfolios, can be represented mathematically as your massive vectors, right? Question number 2 is about your portfolio return calculation. So we have your form here as this one. This is basically your dot product, right? Why not addition or subtraction? Because portfolio return is not your raw asset return. It is weighted exposure to returns. This distinction is very, very critical. Please understand that, right? Which we need to know, right? So that is very, very important. Okay. And again, right, what is important to understand here is that this is, when I say dot product, right? The idea is why other options are wrong, right? Because portfolio, which I told you, right? Portfolio return is not your raw asset return, right? It is weighted exposure to return, and that distinction is very critical, okay? Then we get into this one, covariance matrix. Covariance matrix must always be what? Symmetric, right? Must be. Why? Because covariance of your xy equal to covariance of your yx. Again, deeper thought here is covariance matrix also need to be positive semi-definite, right? Which is not given here, but I'm just telling you. Meaning portfolio variance cannot become negative. Otherwise, risk model become mathematically invalid. The additional point is that your portfolio variance cannot become negative. Then we have eigenvalues and eigenvectors. Eigenvalues and eigenvectors are commonly used in finance as what? Portfolio optimization and PCA. This is foundational to your advanced quant finance. Huge institutional use cases. Bank use PCA for FRDB, risk factor reduction, your stress testing, your yield curve shock, your VOD decomposition, your scenario analysis. And hedge fund use it for your factor neutrality, your kind of what you say, identifying hidden exposure and your seasonality or dimensionality reduction, right? Which you need to know. Okay. Then the next one we have, I think these are the answers which we have already done, right? So same thing. This is answer B, which we had done. Portfolio weight allocation across asset. This is we have taken your what you say dot product. Portfolio return is your dot product, right? We have taken. We have seen that, and then we go to next question. You know, what is important to understand here is simply that covariance matrix, major relationship between asset return. This determines your diversification. most beginner think that more stocks means more diversification. That is wrong. True diversification depends on your covariance. If all assets move together, diversification kind of collapses. This is exactly what happened during your crisis, right? And please understand next part, which is portfolio optimization, PCA, eigenvalue and eigenvectors are used for your uh, PCA, risk factor decomposition, dimensionality reduction. I told you identifying dominant risk factors, right? And in fact, in the previous one also, this is what we already did, and this is for covariance metrics, how assets move together, right? Okay. Overall, the bigger picture here is, which you need to understand, is this chapter may look very basic, but it quietly introduces the mathematical foundation of your Markowitz optimization, your Black-Leiterman model, your PCA, your risk models, your FRTB, your factor investing, your statistical arbitrage, your machine learning in finance, your derivative pricing, your yield curve modeling, right? So many things, right? The entire quant finance universe rests on these ideas. That is why strong quants usually have extremely strong linear algebra foundations, right? So please go back and revise it. That's it from my side. Very, very important to understand. Okay. Please keep that in mind. That's it, guys. I'll see you in the next slide and yeah, next lecture, right? So we'll cover there. Okay. Please go back and revise it. Okay. Thank you.